Hi. So we're going to do assignment 45, which is all about trig linear and angular velocity problems. And gosh, this is really hard for me to do via video because this usually involves me doing all manner of running about the classroom. Um, so yeah, so be patient because I'm not sure how that's going to work here. Okay, we've got two concepts. We have this thing called linear velocity, which you're all very acquainted with. Okay, linear velocity is you driving a car down the street, you biking down the street, you walking. Usually at this moment, I would run across the front of the room. That's linear velocity. Okay, doesn't have to be a straight line, but that's linear velocity. Okay, angular velocity. Oh, wait. Linear velocity is distance divided by an amount of time to get how fast you're going. Remember, distance equals rate times time. Well, if we divide both sides by t, that rate is your linear velocity. Okay? Old concept for us, distance equals rate times time, very middle school. And so we're just considering this now, a certain amount of distance traveled in a certain amount of time. Well, angular velocity is a certain amount of angle you go through in a certain amount of time. Oh, and that's a little omega for angular velocity. Okay, and linear velocity, I believe my notes handout said v. Yeah. So that was our middle school call for it, and now we're going to be talking about linear velocity. All right. Now, that being said, I probably use this formula, I don't know, once, twice in all the linear and angular velocity stuff from now until you take the assessment. Most of the time, though, we're going to be looking for a bridge between these two things. And that bridge comes in the form of linear velocity is angular velocity times radius. Okay, it's not unlike s equals r theta, but instead of s equals r theta, remember our arc length formula? The thing about s equals r theta was these were just quantities, how many miles, how much angle. Well, now we're talking about, that's still radius, but these are rates of change. Radians per minute, degrees per second, and linear velocity, feet per mile, miles per hour, feet per second, meters per year. Okay? So this formula relates these rates for us. That's kind of cool. I have a bridge that allows me to go from angular velocity to linear velocity. And, maybe you want to say, well, I've lived a long time so far, Mr. Kukla, and I've never had a need to relate those two things. And the answer is, well, yeah, but you kind of have been relating them for a long time and just not actually noticed. So, for example, your bike has these pedals and that chain drive system. Ooh, I got some handlebars. And let's have a seat. Okay, so I've got this bike, and this bike is all about me turning that. Me turning that turns the little one here, which turns this one here. That is all about angular velocity. But when I go on my bike, I go down the road. I'm actually having this, biking down the street kind of situation. And so there has to be some sort of bridge between this turning through an angle and this how far down the street we go. And that's what V equals R times omega is. That's the way we can relate these things. And even if you replace the bike with your car, you know that crankshaft in your car is still spinning. It's still spinning through angle, and somehow that is converted into going down the street. You know, you've got that spin, 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 and yet you're going this way. Okay? So that's what we're thinking about. Right? Now, and yeah, don't lose this. And don't lose the fact that this is distance divided by time. And don't lose the fact that this is angle divided by time. Though we'll need that a lot less than we need this. Okay? All right, so when you do a linear and angular velocity problem, you always run into one of two, or almost always, like 90-something% of the time, you're going to run into one of two situations. And we've got type 1. This one is a spinning disk. And in a spinning disk, you're literally talking about being on one spinning object. And maybe you're considering this radius, and maybe you're considering this radius, and maybe you're considering this radius. And I don't really mean radius, but I mean these distances. Well, actually, I kind of mean radius because that's plotting a path in each of these situations. Okay? Now, what do we know about spinning disk? Okay, so let's think about a spinning disk. Let's think about, oh, and this might be a place where I pretend to be an ice skater doing an axle spinning around in place. So, spinning disk. So let's have this conversation. Think about this point, think about this point, and think about this point. And as I make one revolution, if this point starts here, where does it end up after one revolution? Back here again. How about this one? If I make one revolution of this spinning disk, doesn't this point end up back here? And how about this one? If I make one revolution, I get right back here. So what I want to say is the amount of angle that I'm turning through is going to be the same regardless of which of these three I'm looking at. And so I might want to make a statement like this. Well, I think the angular velocities are going to be the same on a spinning disk, because whether I'm here or here and I make one revolution, I've made one revolution. We turn through the same amount of angle in the same amount of time. And so these angular velocities are going to be the same. Well, what about their linear velocities? What if we were to take this, right, and put a little piece of tape here, and then roll the wheel out, and then measure that tape, and then put the piece of tape here, and roll that wheel out? Would this smaller radius circle travel the same linear distance as this one out here? No, I can see that the circumference here is much smaller than the circumference here. And since linear velocity is your distance divided by time, this amount of distance, if we unroll it, is shorter than this amount of distance if we unroll it. So we're traveling through two different distances, but in the same amount of time. And as a result, when we're talking about type 1 problems, the linear velocities are not the same, or we don't expect them to be the same. But the angular velocities are the same. Okay? We're turning through the same amount of angle on a spinning disk in the same amount of time. That's why these are equal. But the linear velocities, no. Okay, type 2. A type 2 problem is often thought of as a connected drive. You know, you've seen this before on your bike. You've got that little pulley system, that little connected chain drive system. Now in this situation, what do we know about the angular velocity? What do we know about the linear velocity? Well, think about when you bike down the street. Like, yeah, there you are, biking down the street. Do the wheels of your bike get further and further apart from each other, or closer and closer together as you bike down the street? And the answer is no. No, they don't. They stay together, right? They're always the same distance apart by whatever the frame has for those. But, you know, what would it look like if they did? It would look like something out of Dr. Seuss, I think, if the wheels got further apart or closer together. So, what we're going to say here is that in this situation, the linear velocities are going to be the same because we're traveling down the street, and this doesn't get further or closer to this. But the angular velocities, I don't expect them to be equal. I mean, I don't know how many of you have tried to bike up Mount Lemon. Yeah. So I never got past mile marker 9. And I'm just going to say, don't do it in jeans if you try and do it. But what I noticed was, as I was trying to bike up Mount Lemon, was that I had to pedal and pedal and pedal and pedal and pedal just to get the wheel to turn over once. The angular velocities were not the same. The amount of angle the wheel turned through compared to me pedaling, yeah, I turned through a lot more angle to get that wheel to go through one revolution. So these are two sets of facts that you need. In a spinning disk, the angular velocities are going to be the same, and I don't expect the linear velocities to be the same. In a connected drive system, yeah, my bike wheels don't get further apart, so I expect the linear velocities to be the same. But crank, 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 I don't expect the angular velocities to be the same. All right? All right. You need this. This, hugely important. And it's hugely important tied to this. Okay? Because we have a bridge between the two. Great. Okay, you got that? You're going to need that. So one last thing. Revolutions per second. Well, this is a type of angular velocity. So is radians per minute. So is degrees per hour. Yeah? However, this one, remember, I told you videos ago that radians is the more common. I mean, it's just like I can't use this formula if theta isn't in radians, because I'll get the wrong answer. Well, guess what? V equals R times omega. No, that's not going to work for degrees per hour. No, it's not going to work for revolutions per second. I need radians. So one of the pieces of information that we need in talking about this linear and angular velocity stuff is the fact that if I'm going to use this formula, I need to convert to radians per time unit. We don't care about the time unit, but the radians is a must. Often, though, in these problems, they tell me you're doing 45 revolutions per minute. Okay, well, that's not radians, that's revolutions. Now, I know one revolution looks like that. So I have a relationship between revolutions and radians, and that is one revolution is always, always, always 2 pi radians. Okay, so if I'm told I'm going 45 revolutions a minute, I want to multiply by 1 revolution. I know it goes on the bottom because these need to cancel, over 2 pi. You could put radians there, but I don't need to because radians is the more common unit of measure. And so I end up with 90 pi as my angular velocity, and these would be radians per minute, because those are canceling. All right, so before I can use this, I need to get out of revolutions, I need to get out of degrees, and I need to get into radians. And really, linear velocity is just going to be this angular velocity times the radius of the wheel, or the radius of the gear. Yeah, so let's see about doing some problems now. Okay, let's see what this looks like now that I've had all this preamble. What does it look like? How do I do it? And I'm looking at this assignment, scatter plots and word problems, assignment 45 in class, trigonometry, linear and angular velocity. The first one is a child spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. Okay, so I know 180 revolutions per minute. Oh, look, revolutions. I'm going to have to convert that to radians. And I've got this situation, there's a little picture of it here. There are some concentric circles. So here's the child, and there's 2 feet of rope, and then we've got a little rock out here. And you're imagining, you're looking down, there's the top of the child's head, and they're spinning in a circle, and, the string is taut and the rock is out there. Okay, but it says here that this child has tied a feather 3 inches from the hand that's holding here. So this is going to be 3 inches. Okay. And then they ask us to talk about linear and angular velocity for each of these things. And this is the feather, and that's the child. Okay. Now, I kind of want to say having 2 different units here is going to screw with us in a little bit. So we're going to talk about that, but not quite yet. So what do we have here? We've got find the angular speed in radians per minute of the rock. Okay, well, we were told that the child is spinning and the rope is spinning, and thus the rock and the feather are all spinning at 180 revolutions per minute. That kid is going to be so sick, so fast. Oh my goodness. But remember, our angular velocity, and that's what we're being asked for here, the angular speed in radians per minute. I've got to convert this revolutions per minute to radians per minute. Now, I know that 1 revolution is 2 pi radians. Does the 2 pi go on the bottom or on the top? And Gary Hawley, my 10th grade chemistry teacher, said, the units you want to get rid of go on the bottom, so the other thing goes on the top. And while he said that wasn't always true, he said that you always wanted these not to be in the same place, so you could cancel them out. So I've got 180 times 2 pi, or 360 pi radians per minute. So that's the angular speed of the rock. That's part A, the angular speed of the rock, right there. But it's also the angular speed of the feather and the angular speed of the child. All of those objects are turning through the same amount of angle in the same amount of time. If they didn't, what would be happening is this would be, lagging behind, and no, that's not what happens when we spin like that. No. So what do we have going on here? Well, I have a spinning disk. And because I have a spinning disk, I know that the angular velocity of the feather, the angular velocity of the rock, and the angular velocity of the child, they're all the same. They're all turning through the same amount of angle in the same amount of time. So I know this answer, 360 pi radians per minute. That's going to be the answer anytime in this question, number 1, they asked me about angular velocity. Oh, look, in part C, they asked me about the angular velocity of the feather. Well, that's also on the same spinning disk, and therefore the angular velocities, they're all the same. But now let's look at parts B and D. They say, what's the linear velocity of the rock? And I say, well, I don't know. I know the angular velocity. My angular velocity is 360 pi. And this is where we need that bridge formula. Linear velocity is angular velocity times radius. Okay, great. Linear velocity equals 360 pi. But what about the radius? Well, so I kind of want to be able to compare these two. And that's in inches, and that's in feet. So either I want to turn this into inches, or I want to turn that into feet. And my experience is students want to turn this into inches. And me, I always want to turn that into feet. 3 inches times 1 foot, 12 inches. And I get 1 foot, 1/4 of a foot. That's what my radius is, 1/4 of a foot. And why would I like to use that? Well, 1/4 of 360, yeah, I don't need to get my calculator. That's just 90 pi. And what were the units here for radius? Oh, feet. This is feet per minute. So this 1/4 is the feather. That's the feather. But what about the rock? Well, the velocity of the rock is still that same 360 pi times its radius, 2 feet. And so we're going to have the velocity of the rock is 720 pi feet per minute. So that's part B, and that's part D. The angular velocities are the same on a spinning disk, but the linear velocities are not expected to be the same because the radii are different. Now, if you'd wanted, you could have turned both of these into inches, but these numbers are then much bigger, and I'd be tempted to reach for a calculator. And you might want to reach for a calculator too, because if mom says, hey, how fast you driving, honey? And you say 720 pi feet per minute, yeah, I don't know about your mom, but my mom is likely to throw something at my head and say, speak English. And so, I would say that in these word problem situations, it might be okay to say 720 pi is going to be 2261.946 feet per minute. Because my mom will have a better sense of this than she will with that pi sitting in there. I'll take either answer. You might want to ask Mr. Paz how he feels about that. So there's problem number 1. We had a spinning disk. Problem number 2, 2 pulleys, and it should probably be pulley wheels. One with a radius of 2 inches and one with a radius of 16 inches. No, with a diameter of 16 inches. Oh, see, it really helps to pay attention. So the radius must be 8 inches. Okay. So what do we want to do? Are connected by a belt. The smaller pulley is rotating at 3 revolutions per minute. Okay, so I'm going to say that this is the small one and this is the big one. Okay, and so our revolutions per minute, that's not a linear thing, that's an angular thing. So this is the angular velocity for the small wheel. Okay, so can we go from the angular velocity of the small wheel to the linear velocity of the small wheel? Sure, by using our little bridge formula, V equals R times omega. So 3 revolutions per minute times the radius, which is 2 inches? 2 inches. Now, why is V not equal to 6? And the answer is because these are revolutions and not radians. You have to convert. Nobody's going to tell you to convert. You have to know to convert. This formula requires that angular velocity to be in radians. What was our conversion factor? 2 pi radians over 1 revolution. So yes, 6 times 2 pi, or 12 pi radians per minute is the linear velocity of the small one. And of course, if you want to decimalize it, that's fine. All right. Now, this is a connected drive system. This is a type 2 problem. What do we know about the linear velocities in a type 2 problem? When you're biking down the street, do those wheels get further apart or closer together? No, they do not. And so then I know that the linear velocity of the big wheel is the same. They're both traveling the same distance. This one goes 10 feet in 5 seconds. This one's also going 10 feet in 5 seconds. They have the same linear velocity. Oops, linear velocity, sorry, inches. Okay, good catch, Cassidy. Good, but the amount of angle this turns through is different than the amount of angle this one turns through. So we use that bridge formula again. V equals R omega. We plug our 12 pi in over here. Our radius is 8. And we're trying to find what the angular velocity is. Well, if I divide both sides by 8, I end up with 3 pi over 2 radians per minute. And that angular velocity is different from this one. This one was 6 pi radians per minute, and this one is a quarter of that. Yeah, a quarter of that. So part A says find the angular velocity of the small wheel. There's the angular velocity. In radians. So 6 pi radians per minute. That's part A. Part B, find the linear velocity in inches per minute. And I believe that's what I had here. Yes, inches per minute. There's the linear velocity of the small one. That's part B. Here's part C. Is it part C? No, this is part D. This is part D, the linear velocity of the big wheel. And then what about the angular velocity of the big wheel? Well, that's this work here. And so we get this for part C. We had to use our bridge formula. Like, we knew the linear velocities were the same. But because this one has a different radius, we knew the angular velocities were not going to be the same. So we did radius times angular velocity equals linear velocity divided by the radius to get the angular velocity by itself, and that's that 3 pi over 2 radians per minute. All right, that's problem number 2. Problem number 3. A merry-go-round is 24 feet across. Okay, 24 feet. The slithering sea dragon is 6 feet from the center. Okay, so 6 feet, we have slithering dragon. The rearing praying mantis is 12 feet from the center. So this is 12 feet, and this is the praying mantis. Carousel is spinning at 1 revolution every 5 seconds. Cool. Okay. And if you want to look up the inspiration for this problem, take a look at the merry-go-round in the Botanical Gardens in Geneva. Oh my goodness. It's the most amazing merry-go-round I've ever seen. Okay, so what's this? Well, this is how fast this is spinning. This is a spinning disk problem. This is a type 1 problem. Now, what did we know in a type 1 problem? Oh, yeah. The angular velocity of the praying mantis is going to be the same as the angular velocity of the slithering sea dragon. These angular velocities are going to be the same. But the linear velocities? No, I don't expect those to be the same. And, I don't know if you've had much experience riding on a merry-go-round, but as a kid, I knew that the cool kids, the kids who wanted speed, yeah, you always sit here because this has the greatest linear velocity. Everybody's turning through the same amount of angle in the same amount of time, but that's the higher linear velocity than here. In fact, here, when the radius is 0, your linear velocity is 0. I know. Yeah, and that's why skaters try and bring their arms in. Maybe not. Okay, so what are we looking for? Part A says find the angular speed of the sea dragon in radians per second. Well, this is the angular velocity everywhere on the spinning disk, except it's in revolutions per second. So let's multiply by 2 pi radians per revolution. And so I've got 2 pi over 5. Angular velocity is 2 pi over 5. And these are going to be radians per second. Okay, so part A, what's the angular speed of the sea dragon? A sea dragon. 2 pi radians every 5 seconds. Okay, part B. Part B says find the linear velocity. Well, okay, I know that linear velocity is angular velocity times radius. And for the slithering sea dragon, the radius is 6. So I'm going to have 2 pi over 5 times 6, or 12 pi over 5. And my units, see those units there? Feet per second. Okay, part C, find the angular velocity of the praying mantis. Well, on the spinning disk, the angular velocities are the same. So the angular velocity for the praying mantis, well, it's going to be the same, 2 pi over 5 radians per second. And finally, part D, we're asked to find the linear velocity of the praying mantis. Well, we're going to go back and use that formula again. Linear velocity is angular velocity times radius. Well, our angular velocity, 2 pi over 5, and our radius for the praying mantis is 12. So I get 24 pi over 5, and my units here are going to be feet per second. Feet per second, or is it per minute? Feet per, well, per second. Yeah, going fast. Okay, any questions about that? That's all of them. On a spinning disk, the angular velocities are equal. So this angular velocity and this one have to be the same. But the linear velocities are different. So when I take that same angular velocity and multiply by the 2 different radii, I get 2 different linear velocities. Okay? Okay. 3 was that one. 4, the tip of a gun barrel. So imagine that this is the turret, and this is the barrel of the gun. And I do want to say, it's really kind of freaky to climb into a 16-inch gun mount on a battleship from World War II. They're just so big, and so many people fit inside them. And they have these long gun barrels. The tip of the barrel is 40 feet from the axis of rotation. So 40 feet. Really big. They shoot for miles. The turret can turn through 124 degrees in 4 seconds. Well, angles per time unit, I'm thinking angular velocity, except, yeah, not if I'm using that bridge formula. I'm going to have to convert that to radians. So I've got 180 degrees in pi radians. And of course, you can tidy this up. I guess that's going to be 31 pi over 180. and these are going to be radians per second. Okay, that's the angular velocity any place on this spinning disk. Find the angular velocity of the tip in radians per second. Oh my goodness, we're already done with part A. Part B, how many feet per second does the tip of the gun barrel move? Feet per second. Feet per second is a linear velocity. Well, I know the angular velocity. Do I know a relationship between these two? Sure, we've got our little bridge formula. V equals R omega. So I'm going to plug in my 31 pi over 180, and I'm going to multiply by the radius of 40. Tink, 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 tink. And I get 62 pi over 9 feet per second. And there's my answer to part B. So there's part B, there's part A. All right, and problem number 5, the last one for us. A flywheel with a radius of 16 inches. Oh, look, another connected drive. Hey, before we read any further, what do we remember about connected drives? This is a type 2 problem. The linear velocities are going to be the same, but the amount of angle that each of them turn through, different. Oops. Angular velocity. So these will be the same. These could be the same if these had the same radius, but they never are for us. So I don't expect those to be equal to each other. All right, so what does it say here? It says here that this one has a radius of 3 inches, and this one has a radius of 16 inches. Okay. And we know the flywheel is turning at 90 revolutions per minute. So I'm tempted to say that's my angular velocity, except why isn't it? Well, it's in revolutions. And I know that this omega always has to be in radians. So don't forget to convert. And so I'm going to end up with 180 pi radians per minute. 180 pi radians per minute. Nice. Now, this is an angular velocity. And here, the angular velocities are not likely to be the same. In fact, I know they're not because the radii are different. But this is the angular velocity for the flywheel. And the flywheel is the big one. Okay, so angular velocity of the big one is 180 pi. Cool. Now that's part A. Find the linear velocity of the big one. Oh, well, we're going to use V equals R times omega. So our linear velocity is going to be our angular velocity times our radius. Whoa, 16 inches. And so 180 pi times 16, I end up with 9047.789. And what are my units? Inches per minute. Don't forget your units on these. And since this is a connected drive system, this linear velocity for here is going to be the same as the linear velocity for here. They have the same linear velocity. They don't pull apart from each other or get closer to each other. They have the same linear velocity. So if I'm going to part C here that says find the angular velocity of the small wheel, well, I know the linear velocities are the same. I guess that means I can actually answer part D first. Part D is 16 times 180, 2880 pi radians per minute, or this decimal approximation, 9047.789 radians per minute. That's the angular velocity of the little guy. But the linear velocity, well, I want to take that. Oh, wait. This is a connected drive. The linear velocities are the same. Oh, this was part D. part d was the linear velocity, v equals. So now, because they're the same, now I'm trying to find the angular velocity of the small one. So I need to say that this linear velocity is equal to the radius times the angular velocity of the small one. So v equals r. Oh, I just wrote that. Okay. So I've got 2880 pi equals 3 times the angular velocity of the small one. And if I divide by 3, and these were inches, my inches here and my inches, that's inches. Yeah. My inches here and my inches here are going to cancel, and I'm just going to be left with radians per minute. Okay, so linear velocity divided by radius is going to give me an angular velocity. And in this one, just to be a little tricky or maybe cruel, we were asked to find linear velocity before we found, we were asked to find angular velocity before we found linear velocity. But in this problem, we know that the linear velocities are the same, and I'm going to need this linear velocity to help me find that angular velocity. Find that angular velocity given this linear velocity and given this radius, no problem to solve for that. I'm just going to take the linear velocity of the connected drive system and divide by the radius of 3. Okay? Well, that's it. There's a worksheet that you will probably be looking at least the one I'm looking at says more linear and angular velocity problems. Yep. More. And then I think, watch out, because I think when you get to problem number 6 on this worksheet, where you're talking about the Dallas-Fort Worth Airport, that's S equals R theta. This is an arc length problem, number 6. Yeah, the others are all angular and linear velocity, and you should be able to find them pretty reasonable and in line with the ones we just did. But watch out for number 6. It's an S equals R theta situation, and remember, theta must be in radians. So you'll need to remember to do that converting, because latitude and longitude are in degrees, and that's what will be given in that problem. Okay, well, I hope you learned something about linear and angular velocity today, and I look forward to seeing you in our next video, where we talk about bearings. Woo! Okay, see you there. Take care, everyone.